Alright, so welcome back to Particle Physics Understand Model. This is lecture 56, and last time we completed our calculation of scattering of E plus E minus to mu plus mu minus, taking them as massless particles with just photon mediation, and we did this without invoking really any QFT, okay, by just using the helicity states of the initial and final states and identifying the correct polarization of the mediating photon. We were able to easily construct the amplitude, right, by taking the appropriate inner products of the electron and muon helicities and the photon polarizations. Okay, so that is what we did, added up the amplitudes correctly, and we found that the m square came out to be proportional to 1 plus cos square theta. In other words, in the center of momentum frame, the differential cross section with respect to solid angle was proportional to 1 plus cos square theta. Okay. That made us wonder whether the scattering is isotropic, and we found that that is not the case. It's not, there is not a 4 pi symmetry here, okay, there is no spherical symmetry here. So scattering is not isotropic, but we still have one symmetry in the problem, which is mirror symmetry, right. If I replace theta with 180 minus theta, because cos square theta is an even function of cos theta, you do have at least a symmetry in the forward and backward directions. Okay, there is a mirror symmetry, and that is not surprising because after all parity is conserved in QED, right, and we did do only a QED calculation, correct. One thing though to note is that there is a symmetry, but nevertheless the process itself favors the forward and backward directions. That is one, it likes going to, the muons and antimuons like going to either 0 degrees or 180 degrees. Okay, that is literally what this differential cross section is speaking out. Okay, and then I finished by saying that if parity is conserved in QED, and that is what is getting reflected here, the fact that parity is not conserved in the weak interactions should mean that if I have the Z boson doing the mediation here, I will see in the cross section that parity is not conserved, right. So this is what we are going to explore a bit in this class, alright, before we go on to other scattering processes. Okay. So we talked about a forward direction, forward meaning again this region in the orange region, and the backward direction meaning theta being close to 180 degrees, right. So if you want to see whether there is any asymmetry between how many events you get in the forward direction versus how many events you get in the backward direction, okay, one can very simply construct a variable or an observable, okay, at colliders, which is, it's called simply the forward backward asymmetry. Okay, and it's a very simple definition. I am going to call that AFB, that is the standard notation for that. I am going to integrate the differential with respect to cos theta, assuming there is a phi symmetry. Okay, so the azimuthal symmetry is there, so that just integrates to 2 pi. Okay, so I am left with d sigma d cos theta still. I am going to integrate it first only in the forward direction, okay, and then I am going to integrate it, let me write it slightly more clearly, and then I am going to integrate it only in the backward direction. What is the backward direction? Cos theta minus 1 to 0. That is clear, right, again from this picture. So all of this is cos theta from 0 to 1, and all of this is cos theta from -1 to 0, right? So okay, that's literally what I'm doing. I'm taking events from that and subtracting that from events in the backward direction. Okay, so I don't stop there. I'm going to actually normalize it to the total number of events. That's it. Okay, I want it to be a nice number that is smaller than 1. So all I'm going to do is take the total number of events. I just integrate from -1 to 1. But instead of writing it that way, just to show that I'm adding events in both hemispheres, I'm just splitting the integral into these two parts. Okay, that is the forward backward asymmetry. And again, just to be clear, I'm going to write this is nothing but the total cross section. The denominator is nothing but the total cross section. Okay. Of course, how would you measure it? You're not going to measure the cross section as such. This is nothing but all the events in the forward direction, which I'm going to call NF, minus all the events in the backward direction, divided by the total number of events. What have I done? All I've done is multiply and divide the numerator and multiply and multiply a luminosity in both the numerator and denominator. Okay, if I multiply with luminosity, I get the total number of events, correct? So that's all I have done here. Okay, so this is how you measure it. In a collider. Okay. Now, for our process, for this, right, with the photon E minus E plus mu minus mu plus, for this particular process, the QED process, what is the forward backward asymmetry? Going from all the discussion we had before, that's just 0, that's it. Right? So you can see this right away in the cross section itself. If I integrate from -1 to 0 or from 0 to 1, they're both the same. That's literally what it means to be an even function. Right? So you can either think of it that way or the physical way where you have parity conservation in QED. So by mirror symmetry, I should have equal number of events in both hemispheres, the forward hemisphere and the backward hemisphere. Right? So that's what this is. Okay. This is in QED again. Okay. But the forward backward asymmetry need not be 0 when I have the weak interactions, when I have, for example, the Z boson coming into the picture. Okay. This is how you measure parity non-conservation, parity violation. So to illustrate that, I'm going to show a plot, okay, of the forward backward asymmetry as a function of the center of mass energy in this problem. Okay. So what is the units of forward backward asymmetry? It's a unitless quantity, obviously, right? So that should be obvious from this, right? Okay. And let me mark off some numbers. This is -1, 0.5, 0. Okay, so let me mark 0.5 more carefully. So I have this 0.5 and then this is minus 0.5, sorry. This is 0.5 and this is 1. Okay. And then on the x-axis, so I'm going to start at around 20, then let me mark a 60, 100, 140, 180, and then maybe just 200, somewhat close to 180. Okay. So, after making a lot of measurements, this is what was seen. Okay, this is actually, first let me draw the standard model prediction for this. Okay, it starts at around 0, then it gets to some negative value, it gets below 0.5, around 60 GeV, it turns around, okay, and at around 100 GeV it crosses 0, and it keeps going, gets a little above 0.5, okay, at around 140 GeV, and then sort of stays constant. Okay. This is in black the standard model prediction for the forward backward asymmetry. I'll explain why you get this in a second. Okay. On top of this, I'm going to draw some data points, okay, from the LEP collider, for instance. Okay. So I may not be drawing this very accurately, but you get the idea. So this is a data point. What does the bar mean? That's literally an error bar. Okay. So at 60 GeV they got that data, and then at around 140 GeV you get this, and then there's some error in the measurement of the energy also, and you know some data is over here. Okay, but the important thing is this is all data coming from the LEP collider. Okay, one little caveat here is that this is actually EE going to BB bar, not really mu plus mu minus, but doesn't matter. In this process you can take BB bar also to be a massless final state. Okay, the point still holds. Okay, now what does all this mean actually? This is actually to me one of the most beautiful plots in particle physics. Okay, it tells so much about the weak interactions, QED and all that. Okay, what does this mean? I'm going to one more time draw the Feynman diagrams, okay, to show what are really the particles involved here. First I have, so this is BB bar now, but doesn't really matter. First I have a diagram with a photon in the S channel, in the mediator, right? And then I have the Z boson. Okay. Now, if I start with my process, okay, with a small enough center of momentum, right, then you agree that most of the process is happening through the photon mediation, right? Why is that? Because the mass of the Z boson, it's around 91 GeV, and that means to see the effects of the Z boson, I need to pump in a lot more energy, right? The Z boson is so heavy that it doesn't really contribute to the process much at small energies. Okay, the Z boson has a propagator and so on. We didn't talk about propagators in this course, but you can intuitively understand. If you have heavier particles doing the mediation, then their effects are going to be smaller, right? We saw this in long range forces and short range forces and so on, right? So in this case, it's like the Z boson is providing a short range force. You are not going to really see it for small energies. Okay. So that is what is reflected in this region of the plot, okay, in this small energy region of the plot. When you start out with, you know, less than 20 GeV energy and coming up to even close to 20 GeV energy, you are mediated mostly by the photon, and so it's mostly a QED process, and that is the reason why the forward backward asymmetry is close to 0. Okay, we saw this, right? Because QED conserves parity. Now, as you go to higher and higher energies, even though you have not really hit the Z boson, okay, you would still have, what do you have? Let me write that. So as I increase ECM, you have interference between these two terms, right, between these two amplitudes, right? Or said differently, your m squared is going to contain terms like these, right? M gamma mz prime plus mz prime m gamma. Sorry, not a prime. Sorry, I'm writing this slightly wrong. M gamma m gamma star, sorry, not prime, mz, right, where star is the complex conjugate, right. So you have interference between a QED amplitude and some other amplitude involving the Z boson, which is a little more complicated. But the point is that because of this interference in this region, okay, you are already seeing the effects of parity violation even before you hit the Z boson properly. Okay, even before you pump in enough energy to make the Z boson in your colliders. Okay, so and it so happens that this interference makes interference between the gamma and the Z makes the forward backward asymmetry negative. Okay, then why does it turn back to some positive value? That's because if my center of mass energy gets to much larger than the Z mass, okay, which is around 91 GeV, right, then m squared at this point, okay, is basically there's a component from m gamma squared that's always there, but it comes the mz amplitude contributes all by itself without much interference. At this point you don't really care about the interference. Okay, so this term, basically what I'm saying is the interference term becomes negligible. So it's purely the Z boson acting as though it's another photon. Okay, but not a QED photon. Okay, it's acting as though it's a massless particle that's mediating the scattering. So that's the reason why it flattens out. Okay, so flattens because no interference, negligible interference. Okay, so it stops dancing around basically. Okay, so that sort of explains the shape of this curve. Okay, and you can ask now exactly what happened in the amplitude for me to get this parity violation. So we know that when you have the Z boson, it's a weak boson, so you should have parity violation. Where can I really see this in the cross section? You might still ask that, right? So I didn't write down the Lagrangian for the Z sector and the W sector in great detail in this course. We didn't really need it for what we wanted to treat here. But here I'm just going to show you one bit of it to see where this cos theta dependence comes from. Okay. So I'm going to write, since so the weak interactions violate parity, okay, that implies the Z has non-universal couplings to left-handed and right-handed fermion states. That much we can believe, right? That's literally what we mean by parity violation, right, at the Lagrangian level. The photon, remember, talk to the left and the right handed fermions with equal strength. We derived this, remember, when we wrote on the QED Lagrangian. But the Z boson doesn't have to, right? This is the origin of what we are seeing in the plot on the left hand side, okay? Because this means you have m square terms, okay, that go like this. I have a coupling of the Z boson to the left handed electron and another coupling to the right handed electron, okay, and in the final state similarly in this case it's a B, right? So I have this, okay, that is the part that multiplies 1 plus cos square theta, okay, and then I have terms like this, GL minus GR E, GLB minus GRB times cos theta, okay. Let's now compare this with what we had in the QED case. Okay, so in the QED case, all I had was just 1 plus cos square theta times e power 4, that's it, right? I didn't care about coupling to left-handed fermions and right-handed fermions, they were all the same. Ultimately, they all turned out to be E, that's why I have an E out in front, E, in fact, in e power 4, okay? But I don't have that luxury here, so you have to write it in this way. And notice that this is still consistent with what we see in QED. Why? Because see the second term, right, this term, right, vanishes if GLE equals GRE, right, and of course GLB equals GRB, right. So like in QED both the left and right handed couplings are the same, so this vanishes and so there is no cos theta, right. So this will make it even function of cos theta. I only have 1 plus cos square theta, right. It's only this cos theta term that spoils the evenness of the function, the mirror symmetry, correct. One more thing to notice is see the second term, yeah, I mean I just said it, it's the second term that produces the non-zero AFB, okay, because it's that is the odd function of cos theta, which is literally just cos theta, okay. So all of this is consistent, right, because you have this term non-zero, that's exactly why you have the AFB going non-zero when you have Z mediation effects coming in, okay. Now this plot, I like this plot a lot because this also really contains a lot of history here, okay. This illustrates the history at least, okay. All this plot with the data all comes from just LEP, but at least it illustrates the history of how we got the Z boson, how we discovered the Z boson, okay. And that history teaches us some nice physics also, okay. So it's worth talking about that a bit, the sequence of the arrival of the Z boson. Okay. So what had happened was in the late 1970s and early 80s, there was a collider called Petra, okay, which was crashing E plus E minus at 30 to 40 GeV of center of mass energy, okay, and of course E plus E minus going to mu plus mu minus, Okay, and they already saw non-zero forward backward asymmetry. So such a simple measurement, right? Okay, and with that they were already able to derive a bound on what the mass of the Z should be. Because if the mass is too heavy, right, you are not going to see the forward backward asymmetry at 20 to 30 GeV, right. By looking at the shape of how the forward backward asymmetry was moving with respect to the center of mass energy, using that they were already able to set a bound on what the mass of the Z should be, that the Z should be maximum 100 GeV to produce these effects. Okay. Then in 1983, they explicitly built a collider called SPS. Okay. I think it stands for super proton synchrotron, but you can check this. Okay. And a gentleman called Carlo Rubbia explicitly built this because they knew that the Z boson had to be less than 100 GeV. So he commissioned building a proton antiproton collider to go all the way to 100 GeV, and just like that they did find the Z boson. Okay, so they found what is called a resonance. Okay, you must be familiar with resonances in other fields of physics. It's the same idea. Okay, you get basically a peak in the cross section with respect to energy. In particular, they found this resonance at this mass. Okay, and that was of course inferred as the Z boson. Okay, of course we know that the actual mass is 91.2 GeV, up to one significant digit, right? Doesn't matter. See, this is still within 2 error bars, 2 sigma. That's very good. That's good enough already. Okay. So I think it's a very beautiful story that you start with, you look at some effects of it at low energies through quantum interference and by constructing this clever variable, and you know exactly, the ballpark where the new boson has to be, and then you go build a collider and basically get the Nobel Prize. Okay, why? Because in 1984, the very next year, Carlo Rubbia and Simon van der Meer got the Nobel Prize. Okay, 1984 Nobel for discovering not just the Z boson, but they also discovered the W bosons this way, which was at around 80 GeV. Okay. Now physics wise, after this, now they had a lot of data. They had the Z boson's properties, at low energies. Now they had literally they had the Z boson being produced in colliders at high energies, right? So now they had all this data. So you just have to now study the angular spectra a lot more carefully, so that you can actually pin down these couplings, right? So we wrote this GL, GR and all this, right, for different fermions, right? So people actually pin down the chiral couplings of the Z boson, but not only that, they also confirmed that the Z boson they discovered was actually of spin 1 actually. Okay, so sorry, and the spin of the Z boson. Okay, and this was of course a wonderful verification of the standard model, because standard model makes all these very sharp predictions, about the chiral couplings, etc., etc. So basically a lot of the Lagrangian parameters of the Standard Model were verified exactly by studying the angular spectra of the Z boson, in addition to studying the Z boson itself, the energy spectrum also. Okay. Now one interesting bit of history here is that, see, only in 1983 SPS was built to directly discover the Z boson, right? But already people were convinced that this entire picture with the Z and W bosons was correct, so that they already gave the Nobel Prize to the people who formulated the Standard Model, the Standard Electroweak theory. Who are they? Three famous names, especially Steven Weinberg, right? And then Abdus Salam and Sheldon Glashow. Okay, so it's important to know that this was awarded even before the Z was discovered, right? 4 years before, right? Even before Z was discovered at the SPS, because just based on the parity violation, right? Based on the parity violation seen from Z gamma mixing. What do I mean by that? Just based on looking at this weird thing, this little thing where the forward backward asymmetry was already non-zero, so the new parity was being violated. They saw that it was matching with what you get from the Z boson and the photon amplitudes interfering. Okay, so I think this is one of the great triumphs of Standard Model and in fact quantum field theory itself. Okay, so we saw another triumph also, which was the discovery of the Higgs boson. That came much later. That came in 2012 because we just didn't know what the coupling of the Higgs was, the quartic coupling. That alone cost us a lot, but also the signatures of the Higgs also were very difficult to catch. Okay, so I'll wrap up the lecture right here. That ends a lot of things that we wanted to learn about the Standard Model. From the next lecture onwards, we'll see how do we know that protons and neutrons contain quarks and gluons. Okay, that's a different kind of scattering. It's called deep inelastic scattering. So that way we'll get some experimental handle on the QCD sector also. Okay, all right. So I'll leave you here. Thank you. See you in the next class.